like to just, you don't have to lock it down. I lock it down anyway, just row 23 because that's row 1. But this part, like, definitely lock down some. Right, so once you have that, so just check as you're checking through, just make sure the formulas in each of these cells are correct in the way that you're going to see the corresponding prenormalization factor for a given n divided by the sum, right? That's what you do. Okay, so we're good. Let's move on. Now we're going to start figuring out how to evolve. So what we have here is basically at 0 the probability, right? The initial probability for each one of those social configurations of little n, right? Now we're going to move to 4. So before we get into any of it, let's set it up, right? If you look at the spreadsheet snapshot that's in the problem set, you want to set up this W up, W down at BB 22 and 23, right? It may not seem like it's important things, like it doesn't affect the results, but it's useful. Just for a moment, ignore the stuff on top. I'll explain why I do this, right? But just have those two titles here, and then you also want n here, right? N is basically this n. It's the same thing. You can just copy it, paste it. The only reason for having it here is just because of convenience, right? Something to refer to, right? Otherwise, it doesn't matter. Okay. And here we are starting to use these two formulas, right? And essentially, this W up and W down is basically those two formulas, right? Which will tell us, how the transition probability evolves over time given the previous probability. Remember that, at each point you have a flux in state I and a flux out state I, and essentially it works on those two, work using those two vectors. So, and really, this is the formula we're talking about, right? Just ignore the stuff bottom. Let's just focus on this part on top, right? What in the slides, what this explains is how do we treat the stuff that's at the boundaries? Because remember, if you look in the slide, each particular point in the position, right, or the probability, there is some probability that's flowing into the neighboring probabilities, right? Neighboring states, right? And then there's some probability that's flowing, flowing out. So there's some probability flowing out and some probability flowing in. But when you are at the boundaries, right, there's nothing that's flowing in from, for example, when you are n at equals to n minus 25, there's nothing flowing from n equals to minus 26 because they don't exist, right? So this is what it tells you, how to treat this. And the way is basically simple, like just get rid of the probability that flows in from n minus 26, right? And the probability that's flowing out towards n equals to minus 26. That's all it's saying, right? But now let's think about this. Now, if we're not on the boundary, if we're any point within, right, besides the boundary, all of this applies. This is basically how the probability at that particular configuration evolves with time, right? So instead of doing the exceptions, let's start working on the. Okay, I'm getting ahead of myself. Essentially what we want to do is let's do the stuff that's kind of in the middle rather than on the side first. But I'll come back to that later. So most important thing we need to figure out is at least what's W up and W down. Like those two things we need to figure out, right? And as usual, I don't like to have a big, chunky, nested formula where things are hidden. I don't know what they mean. So what I'm going to do is I'm going to just break it up a little bit. Like that's how I would have set it up. Like break it up. Let's just look at v n minus n, right? And this exponential delta plus kappa multiplied by n divided by n, which is the first formula here, right? And essentially what we do is chopping it up into two chunks, Vn minus n, and then we have the exponent, right? So Vn minus n is very simple, right? It's just putting in numbers as a formula, right? So nu, and n, big N, are stuff that we have in our input all the way to the left, this stuff, right? So just put them in, right? So what I'll do is have the before, which is my new outside open bracket, multiply into my big N. All of those are, absolute references, right? Never changes with wherever you are. And then minus little n, here. Little n is going to change. Remember, little n always changes, right? That's the thing that varies. So for this, we just want to lock down the rows and let the columns change so that over time, if I look at my columns, they move, but all the other stuff, they stay constant, right? They stay fixed. And then the other stuff, also very easy, exponential, right? It's just delta. I'm going to refer back to my delta here, plus my, and here I put it in brackets just because, just keep it clean. Kappa times BC is going to be my little n again divided by the big N. So little n is reference relatively, and then big N and my kappa is always going to be fixed. And I'm going to have this, right? So the combination of these two, the product of these two, is going to give me my this, right? My W. Right? So these two multiply together, put it up, I'm done. And the good thing about doing it this way is, let's look at W down. W down is essentially not that different from W up, right? We're just flipping some signs here, right? We're flipping this sign, and then we're flipping the signs within here, right? So if I have all the formula here, what I can do is just select all of them, just highlight them, copy them, and just throw it down here, right? Everything still works, right? But now all I do, instead of writing everything over again and trying to find the references and then potentially making a mistake somewhere along the line, I minimize my mistake by just putting a plus sign. Done. So very easy. Same thing here. Copy all of this stuff. Go in here. Right, and then this is just put a negative sign, so just put in bracket like parenthesis for all the values that in the exp exponent function. Put a negative sign in front of it. You're done in it, right? So that's essentially it, right? So that's a quick way. Yeah.
What does that exp exponential function do?
It's basically, this is a mathematical function. It's your e to whatever. That's what it does.
Gotcha.
Yeah. So yes. Yeah. So that's essentially what it does. That's all. Like super simple. Like I feel this is the most least error prone way to do it. And once you're done, right, it's just multiplication. You're done with here. Copy them over for all your n from n to n equals to negative 25 to 25. You're done. So okay, big part of the problem solved, right? Now let's look at dp/dt. So this is the part that we actually want. We actually want where here the purpose of us doing here is to calculate dp/dt. And here's what we're talking about, right? So dp/dt, basically all of this stuff kind of gives you dp/dt, right? But it tells you that at the boundaries, this stuff might be slightly different from the stuff, or they are different from the stuff that's in the middle, right? So all except the boundary, everything else is the same. So instead of doing the boundary first and adding on stuff later, the kind of easier way is to just let's start in the middle, right? Let's start in the middle and deal with the more generalized formula here. And what we're gonna do, we're gonna take this formula, right? Instead of removing all of this, we're gonna just leave them there. And essentially, if you notice, like the way I've set it up my formula, so if I'm looking at here, it's in the exact order of this stuff here, right? There are 4 parts to it. I'm setting up exactly the way here, right? And let's kind of break it down. Here, that's what I've done. Let's break it down. All right. So first of all, we're gonna deal with this. We're gonna deal with this W down for n plus 1 multiplied by the probability of n plus 1 at time t, and let t be 0 in our case, right? Because we're looking at the first one. So it's simple, right? We have already calculated W down for all of the values. Now we are working in our column at n minus 24 because we don't want to work on the boundary